Okay, before we get into doing calculations with this unit, we're on the top of page 17, and let's talk about something real simple, something called a solution test. And suppose you're given a test tube with a solution, and they ask you, how can you tell if the solution is saturated, unsaturated, or supersaturated? Okay, so what you do is you take a small crystal of whatever's dissolved in here, small crystal of the solute, and you add it, you drop it into the solution. Now, if that crystal dissolves, then you know that before this crystal dissolved, there was more room for it, if you will. In other words, the solution was yet to be saturated, or it was unsaturated. All right. On the other hand, if that small crystal doesn't dissolve, then that leads you to conclude that the solution that you had was saturated. And if that small crystal causes other crystals to come out of solution, more than what you started with, then that solution must have been supersaturated to begin with. All right, so there you have your three types of solutions. And one other thing you should note, when you do this demonstration, which you may have done this in class, it would be very memorable, and then the solution is passed around. In the case of the supersaturated solution, it gets hot. And the reason for that is because crystallization, that is when the crystals come out of solution, is exothermic. Just as for most solids, dissolving is endothermic, crystallization overall is exothermic. So because crystallization is exothermic. In other words, it releases heat to the surroundings. And now you're going to need your calculator and the periodic table in hand, because we're going to have to do a formula mass soon. There are two ways to express concentration in this course, and that is molarity, big M, which is the moles of solute per liter of solution, and parts per million, ppm, which we'll deal with in a second. So for molarity, the formula is in the back in table T. You'll find it under concentration, and molarity is, again, the moles of solute divided by the liter of solution, or liters of solution, so moles per liter. And you have two types of problems here. You have the easiest kind of problem, such as this one. How many moles of NaCl are in 2 liters of a 2-molar solution? So this is the easiest because they tell you the volume and they tell you the molarity. And the only question is here is the moles that you're looking for. So it really doesn't matter what the compound is that you're dealing with here, because this has nothing to do with the gram formula mass. So plugging it in, since molarity is moles per liter, 2, the molarity, is equal to X, the moles of the unknown, over 2 liters. And just cross multiply, and you end up with 4 moles. And then let's go to the hardest kind of molarity problem. And that's where instead of giving you moles, they give you grams. For example, 45 grams of C6H12O6 in 250 milliliters of solution. So the first thing we could do is, before we start doing a mole calculation, is let's convert these 250 milliliters to liters by simply moving the decimal place 3 places to the left. Because if you recall, 1 liter is 1,000 milliliters. So you're dividing by 1,000, so you get 0.250 liters. And then for the 45 grams of glucose, you're going to first have to get its gram formula mass. So you're going to look up in the periodic table the carbon, the hydrogen, and the oxygen. And then add those up, and you should get 6 times 12 for carbon, 12 times 1 for hydrogen, and we'll just go to the nearest whole number, and 6 times 16 for oxygen. So you get a gram formula mass here of 180 grams per mole, which means that a mole of glucose, which is what C6H12O6 is, weighs 180 grams. Then, if you recall, in a mole calculation, the number of moles is equal to the given mass divided by the gram formula mass. So 45 grams divided by the 180 grams per mole will give you 0.25 moles. And finally, the third step, and this is a lot of work for a simple problem, the third step is to take the 0.25 moles divided by 0.25 milliliters, and you get a 1 molar solution. So we'll do one of those two later when we do problems again. And then when it comes to parts per million, you have the formula there also. Wow, that's big. Parts per million, or ppm, is the grams of solute divided by the grams of solution times a million. I want to remind you that the grams of solution is the grams of solute, what's being dissolved, plus the grams of solvent, substance doing the dissolving, which in this course is almost always water. So let's take a look at this one here. Given a 300 grams of a solution containing 0.0100 grams of solute. So find the parts per million. So this is a simple plug-in. It's the 0.01 divided by the 300 times a million, and that gives you 33 parts per million. And finally, before we begin doing a set of problems, the last word on solutions is remembering the effects of salts and sugars on the freezing point and boiling point of the solvent. So salts and sugars don't evaporate easily, to say the least. So salts and sugars are considered non-volatile solids, which means they don't evaporate. And salts and sugars, when dissolved in water, will raise the boiling point and lower the freezing point of the solution. So if it's pure water, you'd expect it to freeze at 0 degrees Celsius and boil at 100 degrees Celsius. But when you add sugar or salt to that, the boiling point increases and the freezing point decreases. So another way of thinking of this is, since this right here is the liquid range, and from this point on you'd have gas and solid, adding salt or sugar will actually extend the liquid range. And of course, the more concentrated the solution is, the more solute you have to solvent, which is really what a concentration is, a ratio of solute to solvent, or to solution, I should say, the greater the effect. So another way of saying that is, the saltier or the sweeter, the higher the boiling point and the lower the freezing point. So for example, 100 grams of salt and 500 grams of water is going to have a lower freezing point than 25 grams in 500 grams of water, since this is more concentrated. It contains more salt to water. And then you want to remember one other thing about salts is the fact that salts have a multiplying effect on boiling point and freezing point. And the reason for that is because salts, if you recall, when we started this discussion on solutions, salts split. And when the water dissolves the crystals of salt, it divides it into its ions. So in order to answer a question like this, if you're given 1 molar solutions of these different solutes, you'd have to find out the number of particles per unit of solute. So in the case of glucose, when you dissolve this, it doesn't split. All right, what you end up simply is with C6H12O6 aqueous. So that only gives you one particle for each unit of glucose. But the sodium chloride splits and ends up giving you sodium plus and Cl minus aqueous. So that gives you two particles. The calcium chloride, when it splits, gives you, notice, two Cl minuses and a calcium plus 2. So that gives you three particles. And the last one, the aluminum chloride, when that splits, you get an aluminum ion with a plus 3 charge and three chlorides, as you can tell from the subscript there. So that gives you four particles. And clearly the aluminum has a greater number of particles in solution, so the aluminum will have the greatest effect on the freezing point and boiling point, and in the other extreme, the glucose would have the least effect. So this would be the number of particles in solution. Okay, that wraps it up for solutions. What I want to do next is to do a set of problems on this, and you can either take a break, go over these notes again before we do that, or you can go ahead of me and do some problems, and then I'll catch up to you.